So we're starting now. So today, we will continue our discussion with parsing, and today we'll talk about, one parsing technique or one approach to parsing, which is top-down parsing, and more specifically, we will be talking about what is called LL1 parsing. So LL1 parsing will not become clear until we present the actual algorithm. But LL1 here, the first L stands for scanning the input from left to right. So this is scan input from left to right. And the second L stands for leftmost derivation. And what do you think the one is?
One character look ahead?
Yeah, exactly. So it's one character look ahead. So it's one character or one symbol look ahead. So this is the parsing technique that we will be studying today. So what we did last time is that we reached at this grammar for generating expressions in a typical programming language with the basic arithmetic operations, multiplication, division, addition, and subtraction. And we talked about the challenges of building a parser for this. And a parser is a program or an algorithm that will automatically find a derivation for a given input string. So it will either find a derivation for a given input string and build the parse tree that will become the abstract syntax tree, or it will say that this input string does not belong to this language. It's an invalid input string. There is a syntax error in it, and I can't parse this. Okay, so a real compiler will either print an error message that your program has some syntax errors, or if your program is syntactically correct, it's going to build the abstract syntax tree, and then this abstract syntax tree will get used for code generation. And with this form of the grammar, we faced two problems. The first problem was with the left recursion, because if we tried to build a parser or a parsing algorithm for this, an algorithm is a set of systematic procedure for solving a problem. So it's a well-defined sequence of steps for solving a problem. And if this algorithm is very systematic, it's going to keep substituting expression plus term for expression forever, and it will have a problem. It will go into an infinite loop if it keeps systematically substituting this for this. So that's why left recursion will cause a problem to a parser if it's based on leftmost derivation. If it's a parser that is based on leftmost derivation. The other problem is that even if we somehow solve this infinite loop problem, and if we avoid systematically making the same substitution, the problem is in identifying the right substitution when there are multiple rules or multiple productions that define a certain variable or non-terminal. Here I have 3 of them. Which one is the right one? So parsing is about determining which substitution is the right substitution for the input that I'm looking at. And with this form of the grammar, we couldn't parse, an example string. We couldn't deterministically decide which substitution is the right substitution. So when you can't deterministically decide which substitution is the right substitution, this means that you will try one substitution and then go with it until you either find a correct derivation or hit a problem, discover that that substitution was wrong, then you will backtrack. And you will go through all the substitutions that you made and try to identify the substitution that was wrong and try another substitution and so forth. But with this backtracking, parsing will not be efficient at all. It will be, basically we'll be talking about exponential time. The time will be exponential in an exponential function of the size of the depth or height of the parse tree, because the number of nodes in a tree is an exponential function of the height of the tree. So that's not an option. That will be too slow. So what we are looking for is a parsing algorithm that does not backtrack. So we're looking for a backtrack-free parser or predictive parser. A predictive parser is a parser that can determine, based on a limited number of look-ahead characters, and in this case it's going to be one look-ahead character, based on one look-ahead character, which substitution is the right substitution. And towards the end of last lecture, we pointed out that one technique that will work on this grammar is converting this grammar from the left recursion form to the right recursion form. This will work, and in fact, in today's lecture, we will do this, and we will understand why when we convert this from the left recursive form to the right recursive form, things will work out well. So this is something that people have figured out, decades ago. So this is, people have found that the right recursive form of this grammar will work well with an LL1 parser. So again, let's review converting left recursion to right recursion. So if you have, this is what we call left recursion elimination, or conversion of left recursion into right recursion. So if you have something like x equals x alpha or beta, again, if you do the derivation, some derivations, you'll do x alpha, and eventually you will do a beta. So a string that is derived, one valid string derived from this is beta, alpha, alpha, alpha. Okay? So this grammar can be written in an equivalent format, which is x is beta followed by any number of alphas. So beta is going to be first, then x prime, where x prime is any number of alphas, but now I can use right recursion instead of left recursion. So I can do alpha x prime or epsilon. So these are two equivalent formats. In fact, I can generalize this. In general, I can do x if x equals x1 alpha 1 or x2 alpha 2 or xn alpha n or beta. This is equivalent to what? X equals. So in general, if there are multiple productions for multiple left recursive productions for x, then how do I convert this to the right recursive format? I will still have the beta in the beginning. Any of them will have to start with a beta. So it's going to be beta x prime, where x prime in this case is. So we'll just do the same thing for each one of them. So it's going to be alpha 1 beta is going to be alpha 1 x prime or alpha 2 x prime or alpha n x prime or
Beta. No.
or
Epsilon.
epsilon.
Epsilon, yeah.
Epsilon. Okay, so this is the general left recursion elimination. So this is the left recursive and this is the right recursive. Now, can you see the intuition now? Intuitively, why is this right recursive format, why is it going to work better with parsing? Remember that parsing is about trying to match an input string with a grammar. So why? What's the intuition?
Because it's not really recursing. It's going more into a loop because you have the first character first, or first symbol first, which is the beta. Then it goes down to the x prime, and then you can have one, none, one, or more of the following symbols.
Yeah, but this is still recursion. So this is still recursion, and this is still a loop. You know, recursion is basic.
It loops back in on itself, but it's not as messy.
Okay. So why is, you're trying to match this string with a grammar. Why will this work better? Look at this. This is your string. And you have this rule. And you have this. Look at this. So at least, this here, it's exposing the beta, right? So it's exposing this beta that is that must appear at the beginning of the string. It's making this exposed explicitly. This is explicitly saying that a string that is derived from this grammar must start with a beta. It's obvious here that the string must start with a beta. Here it's not as obvious. It's saying, it's x alpha or beta. So it's not as obvious here. It's not as explicit that a string that is derived from this must start with a beta. And the start is very important, but because what we are trying to do is to match an input string with a grammar given the look ahead, the first character or the first symbol in the string. So let's see now how this is. So this is the intuition. So let's now apply this rule. Let's apply this general rule to the grammar that we have, to the classic expression grammar, and see how we can convert it. So this is the left recursive format. Now, the right recursive form right recursive form is the following. So now here, matching this with this rule, where is x? X is what? X is the expression, right? X is our expression. So this is x. So where is alpha 1? No, it's plus term. So plus term, this is alpha 1. Okay. And this is another x. And this is, what's this?
Alpha 2.
Alpha 2. And what's term?
Beta.
Beta. So we only have two alphas in this case. This is the general formula. In this grammar, we only have alpha 1 and alpha 2. And this is our beta. Now, based on this rule, what should be the right recursive form of the grammar? Expression equals or term
Expression.
exactly term expression prime, where expression prime is so alpha 1 x prime. What's alpha 1? Plus term. plus term expression prime or minus term expression prime or epsilon. See, the point is that this form of the grammar is more human readable, right? It makes more sense. It's more straightforward. This looks odd.
Yeah.
The right recursive form looks odd, but in fact it will work much better for parsing, as we will see in a minute. Okay, although it's it looks odd. Yeah.
Couldn't you put the plus and minus orum and have that in a curly brackets too, as part of the grammar language? Because I've seen that done too.
Okay.
You put plus
Yes.
or minus and put them in curly braces, and then
And-
you just have the one term expression prime and then or epsilon.
Okay. Yes. But it will not. Yeah. We can do this. It will not help us with the parsing,
Yeah.
but yes, you can do it.
Yeah.
Okay. So now with the term should be now straightforward. We can do the same thing with the term. So tell me what to write. Term is factor term prime, where term prime is term prime is multiplication factor term prime. Let me write it a little bit smaller. Use the space. Multiplication factor term prime or divide factor term prime or epsilon. Now, how about factor? Does it have any left recursion? No, factor does not have left recursion. Factor does not appear on the right-hand side. We don't have recursion at all. In fact, we have indirect recursion here because we have expression, but it's not a direct recursion. So its factor stays the same. Identifier or number or expression. Okay. So this is the right recursive form. It looks odd, for someone who sees this for the first time. It looks odd, but we will see how it will work nicely when we use it for parsing. So let's see how we can parse this string, this expression, x plus 5 times y. So this is an expression. This is the correct expression that can be derived from this grammar. So let's see how we can use this right recursive form to do parsing without backtracking. So we will see that we will not have to do any backtracking. It will always be obvious what the substitution should be. So this is a top-down parsing. So right now we are doing top-down parsing. And what top-down parsing means is that we start from the start variable. So we start from the top, and we work our way down the tree until we get to the leaves. So top-down, we start from the start variable, top. So, okay. So we say, okay, expression. Now what should we substitute for expression? There is only one production. So it's obvious. There is only one production, so we substitute term expression prime. Now it's a leftmost derivation. So should we look at term or expression prime first? Term, because it's leftmost derivation. So we look at term. what can we substitute for term? Again, there is only one possible substitution, which is factor term prime. Now, what's the next variable that we should factor? So now factor,
Turns out to be an identity.
what are the substitutions for factor? There is an identifier, a number, and an expression. Now, an identifier, these are terminals. For our language, these are terminals. So identifier is one terminal, number is another terminal, and here, where's the terminal?
The left
The open parenthesis. So this is the terminal. Expression is a variable, is a non-terminal. This is a terminal. So based on what we are seeing in the input here, the next in the input, the scanner will identify this as an identifier, right? So this is identifier, this is plus, this is number, and this is another identifier. Plus. So this is what the scanner will tell us. So now we're looking at the input. We're seeing an input, an identifier in the input. And at this point, there are three possible substitutions, and only one of them starts with an identifier. So this is the only substitution that can be right. This cannot be right because this starts with a number. And this cannot be right because we're not seeing open parentheses. So the only correct substitution is identifier. And in this case, the identifier is X. Yes, what's the question?
So the parser, when it executes, the first thing it sees is the identifier, right?
Yes.
So how does it know to start with expression instead of starting with factor?
Because it's top-down parsing. You always start with the start symbol, start variable. So factor is not the start variable. So that's why it's top-down. Top-down, it means always start with this, with the start.
Always start with an expression then?
Always start with the start variable for your grammar. And the start variable for this grammar happened to be expression.
Okay.
So top-down parsing means you start with the start variable, always. We're trying to build the tree, in a top-down manner. So the root of the tree will always be what?
Expression.
The root of the tree will be expression for this grammar, and in general, it will be the start variable. The grammar's start variable in general. Okay. Now now since we have read the X, now we have consumed one word from the input, and now our pointer in the input string is pointing at the plus. So because we have already consumed this, right? Okay, so now term prime, for term prime, you have three possible substitutions. One that starts with multiply, one starts with divide, and one starts with epsilon. Which is the only one that can be correct?
Epsilon.
Epsilon, because I'm not seeing a multiplication or a division. I'm seeing an addition. So term prime, I'm going to substitute epsilon, and it's the only option that is right. Okay, so now for expression prime, I have three possible substitutions. So I have plus, I have one that starts with plus, one that starts with minus, and one with an epsilon. And what I'm seeing here is a plus, right? So in this case, I will just use the one with the plus. So it's going to be plus term expression prime. Now there is something. Let's put a question mark here, because this substitution, in fact, is questionable. It is the right substitution, but there is something that we are missing here. We know we're trying to find the substitution for expression prime. We have one that starts with plus and one that starts with minus. We know for sure that this is the wrong substitution. But what about the epsilon? The epsilon is not necessarily a bad substitution. because it could be possible. It's not possible in this particular example, but in general, it may be possible that, to substitute epsilon, which is nothing, for expression prime, and then the plus that we are seeing in the input is not a substitution for expression prime, it's a substitution for what comes after expression prime. So generally speaking, and this is something that we will discuss in detail when we look at the the conditions under which this kind of parsing will work. So the point here is that it's to look at the possible substitutions. I know for sure that this is not right because I'm not seeing a minus, but this may be right if the plus sign that I'm seeing in the input belongs to something that can come after an expression prime. So in other words, I need to do an analysis that tells me what can possibly come after an expression prime in this grammar. And this is what we call the follow set. We're not going to do them right now, but we'll do them later. So we need to know the follow set. So there is the first and the follow. So the first is the set of symbols that can appear in the beginning of a string that is derived from x. So let first of x, set of terminals that can appear as first symbol in a string derived from x. So this is first of x. So I assume that you have seen first and follow.
Yeah.
Okay. And follow of x is the set of terminals that set of terminals. The follow of x is the set of terminals that
come immediately after.
Yes, can appear immediately after a string derived from x. That can appear immediately after a string derived from x. Now, why is this interesting in this case? Trying to find the substitution for expression prime. So now, in terms of the follow set, under what conditions will epsilon be a valid substitution for expression prime in this case?
Closing parenthesis.
Under what condition will the epsilon be a valid substitution for expression prime in this case?
No plus or minus. No plus or minus.
Using the first and follow sets, in terms of first and follow sets. So epsilon will be a valid substitution for expression prime if plus belongs to the follow set of expression prime. If plus belongs to the follow set of expression prime, this means that for now I can substitute epsilon for expression prime, and this plus that I'm seeing belongs to something after expression prime. So it's like, here I'm having, at this point I'm having an expression prime, and this plus belongs to something else that belongs to the follow set of expression prime. But as we will see when we do the first and follow set analysis, in fact, plus does not belong to the follow set of expression prime. So plus, the epsilon substitution will not be a valid substitution. Okay, so we will fully understand this after we compute the first and follow sets. So let's now continue this derivation. So now this is the right derivation. I have consumed the plus. So when I consume the plus, I advance the pointer here to 5. I have consumed two symbols from the input so far. Now I'm looking for a correct substitution for term. And term, there is only one option, which is factor term prime. Factor term prime. Now I need a substitution for factor,
Number.
identifier, number, and based on what I'm seeing, the only correct substitution is number. Because I'm not seeing an identifier and I'm not seeing an open parentheses. So this factor is going to be a number, and this number is 5. Number is 5. And now I need a substitution for term prime. Sorry, I have consumed the number, so I have to advance this because I have already consumed the 5. Now I'm looking at, my look ahead symbol at this point is the multiplication. Okay, so for term prime, multiply, divide, epsilon. Divide, I know it's not correct because I'm not seeing a divide. I'm seeing a multiply. So multiply is a possibly correct substitution. But epsilon could be a correct substitution if epsilon could be a correct substitution in this case if
Yeah, it's in the follow
The
set.
follow set.
if what is in the follow set of what?
The multiplication.
Yeah, the multiplication is in the follow set of term prime. So if the multiplication is in the follow set of term prime, this would be a correct substitution. But in fact, as we will see in a minute, it's not. It's not in the follow set of term prime. Intuitively, a term cannot be followed by a multiplication because a multiplication will be in the middle of a term. It cannot. A multiplication cannot appear after a term. Okay. Now, so the correct substitution is times factor term prime, and I have consumed the times the multiplication. I'm looking now at y. So now factor, what's the correct substitution? I'm seeing an identifier, so it's an identifier. And I have consumed everything now. So in fact, what I'm looking at is the end of file. So there is an end of file at the end of each string. Okay. Now term prime, I need a substitution for term prime. And I'm not seeing anything in the input. So I'm not seeing multiplication or division. The only correct substitution is an epsilon. And what's left?
The expression prime.
Expression prime.
And that's going to be an epsilon.
I'm not seeing a plus or a minus. In fact, the string is done. I have passed the string, so I'm not seeing a plus or minus. Then it's going to be an epsilon. Okay. So this is a backtrack-free parser. So at each step, I was able to deterministically decide which substitution is the right substitution. So I did not have to backtrack. I didn't make decisions and then undo them and backtrack. So this kind of parsing, this will work well under what condition? So when do you think? Of course, this does not parse all the languages in the world.
No.
So under what conditions? Yeah.
In a language where you only need to see one symbol in front of you to know what to do.
Okay, and when will that be possible? So given a grammar, if I give you a grammar, can you tell me beforehand whether this type of parsing will work on it or not? So by looking at this grammar, can you tell?
Not easily.
Yeah. Okay. In fact, we cannot answer this question until we compute the first and follow sets. It has to do with the first and follow sets. Basically, we are looking at the first of this and the first of this, right? So we are looking at the first of each alternative that we have. So we have these alternatives, and we look at the first of each one of them, and we're trying to match the first with the look-ahead symbol. So if there is an overlap in the first symbols, we know that this is not going to work. So if we had a plus here and another plus here, two alternatives that have the same start, the same first symbol, then we know that this is not going to work. But we also have to look into the follow, because if there is an epsilon, then substituting an epsilon may be correct if what we are seeing in the input is a valid appears in the follow set of this. If what we are seeing in the input appears in the follow set of this, epsilon will be a valid substitution. So let's now compute the first and follow sets. Okay, so for the first set, it will be easier to start with the lower level. In computing the first, it will be easier to start with the lower level non-terminals or variables. So first of factor is what? Identifier or number or open parents. First of term prime. First of term prime is multiplication. I'm not going to put the comma here in the set because the comma may belong to the terminals. It may be one of the terminals, so I will not put a comma. So it may be multiplication or division or epsilon. So it can start with an epsilon. First of term. Now the term is factor term prime. So the first of term is going to be the first of factor, which is identifier, number, and open parens. Now, is it always true that if I have, generally speaking, if I have x drives y, z, then the first of x will be the first of y? Is that always the case?
If y is epsilon,
Yeah, if y is epsilon, then
the first of z is part of.
then I look at the first of z, right? So generally speaking, if what comes after y, if y itself has a epsilon in its first set, then I should look at z. Generally speaking, if you have x, a1, a2, a3 through an, so as long as you have epsilon, if this has epsilon, if a1 has epsilon in its first set, then you should add the first of a2. And if a2 has epsilon, you should add the first of a3. Why? Because these may vanish, and an x may start with an a3. Now, in this case, our a1 is what? Factor. And does factor have an epsilon in its first set? It does not. So I just stop at factor. Okay, we'll do more examples, by the way, on first and follow. So in this case, I will stop here. First of expression prime is plus, minus, or epsilon. First of expression is the first of expression. Expression starts with a term. So I look at the first set of term, and the first set of term has identifier, number, and open parents. Should I look at the first set of expression prime? No, because epsilon does not appear in the first set of terms, so there is no way of bypassing term. You cannot substitute an epsilon for term, so an expression must start with a term. An expression cannot start with expression prime. Why? Because epsilon does not appear in the first set of term. Okay, so this is for expression. Yeah. So this is all what we need. So now let's look at the follow sets. Follow set. Now for the follow set, it's easier to start from the top. So follow of, by the way, it's an iterative process. So you have to, in general, you have to keep iterating until you get to a fixed point, until no more changes are possible. But with these examples, with this particular example, one iteration is possible. So what's the follow of expression? The follow of the start variable is always,
Expression prime.
the follow of the start variable is always, generally for any grammar, the follow of the start variable is always,
Epsilon.
no, end of file. Because this is, no matter what you are deriving, so this whole thing is going to be an expression. This is what you are trying to do. This whole thing is an expression. So expression is your start variable, which is the biggest thing, the root of the tree. So after the root of the tree, you will always have the end of file. So end of file. But in fact, if you look at the right-hand side, there will be other symbols that can appear in the follow set of expression. What appears on the, what appears after expression on the right-hand side?
Closing parentheses.
Close parentheses, yes. Now follow of expression prime. Now, in order to find the follow set of a variable, you look at the variable on the right-hand side, not on the left-hand side. You look at it on the right-hand side. Here's an expression prime. So you see what comes after it. And you look at the first of what comes after it. Now here, nothing comes after it. So I don't have to add the first set of whatever comes after expression prime. So if I had an x after expression prime, I would have put the first set of this x into the follow of expression prime. But nothing appears after expression prime, so I don't have to worry about this. But I have to worry about, so there is another factor. Expression appears at the end, expression prime appears at the end of expression, which means that I have to add the follow set of expression to the follow set of expression prime. So I have to add end of file, because this whole thing is an expression, and this is saying that expression prime may appear as the last variable in expression. So it means that here you will have an expression prime. So if you have an expression prime here at the end of an expression, then in the follow set of it, you should put everything that is in the follow set of expression. Okay, question? Okay, so I keep searching for expression prime on the right-hand side. Here, expression prime is expression prime, so this is not going to give me anything useful. Then I don't see any more expression prime. So then I move to term. Follow of term. Now, where does term appear on the right-hand side? It appears here. So what comes after it is an expression prime. So what should I add? First of expression prime, except for epsilon. So first of expression prime is going to be plus and minus. Plus and minus. Epsilon never appears in the follow set. It doesn't make sense for epsilon to appear in the follow set, because the follow set is about answering the question, what comes after this? And you can't say nothing. You can't say nothing comes after it because, if it's the end of the string, then what comes after it is end of file. So it doesn't make sense for epsilon to appear in the follow set. So here, term appears here. I put the first of expression prime. Then I keep scanning for term, followed by expression prime. Doesn't add anything new. OK. Sorry. Term here, I have to not only look at the first of expression prime, but I also have to take into account that expression prime has an epsilon in its first set. So expression prime may vanish. I can substitute epsilon for it. And if it's possible to substitute epsilon for expression prime, this means that term can be the last thing in an expression. And if term can possibly be the last thing in an expression, I must add the follow of expression to the follow of term. Why? Because this thing can vanish. This has an epsilon because of this epsilon. So in the follow set of term, I have to add everything in the follow set of expression, and that's end of file and close parentheses. Now follow of term prime equals OK, so I look at term prime, scan for term prime on the right-hand side. So it appears here. What does this tell me? Put the follow of term into the follow of term prime, because term prime can be the last thing in a term. So I just copy the follow of term. OK. Is there another term prime? Here, this tells me add the follow of term prime into term prime. So this is not going to be useful. And here, I don't have a term prime. Then I look at the follow of factor. Again, I scan for factor on the right-hand side or the left-hand side. The right-hand side. So this is the left-hand side. This is the right-hand side. So where is I scan for factor? Here's a factor. It's followed by a term prime. So I put the first of term prime. So the first of term prime is going to be first of term prime, multiply, divide, and I never put an epsilon. But this also tells me that term prime, since term prime can have an epsilon, can disappear. Factor, if term prime can disappear, this means that factor can be the last thing in term. If factor can be the last thing in term, then factor can be followed by whatever term is followed by. So I put everything in the follow set of term into the follow set of factor. And that will add everything. Plus, minus, and end of file, and close parentheses. In fact, these are all the symbols, so it's not going to get any bigger. Again, if I look into factor, it's followed by a term prime. This is not going to add anything because it already has everything in it. So this will be the end of next time we'll go through another example for first and follow set. We will try to, I wanted to finish this before the end of the lecture, but next time we'll go through another example on first and follow set, and we will, give all the rules for finding the first and follow set, so that we can understand the general procedure for computing first and follow sets. But remember here, it's going back to these three possible substitutions. Expression prime cannot be followed by a plus, so the follow of expression prime does not have a plus in it. This means that now I can exclude this epsilon.